At its core, computer science grapples with a distinct separation of states. On one side, you have human thought, complex, abstract, and highly contextual. On the other, you have machine computation, rigid, binary, and executing strictly defined logic. These two environments do not inherently speak the same language. To bridge this gap, we rely on an operational boundary layer. This line between the user and machine states is where translation occurs. This space is the user interface, or UI. It uses applied psychology and systems architecture to facilitate the exchange. The primary objective of UI design is to construct a pathway for communication between human and machine that is efficient, accurate, and reliably learnable. Achieving this requires minimizing cognitive load, the total amount of mental processing power a user must expend simply to figure out how to operate the system, independent of the actual task they are trying to accomplish. When cognitive load exceeds a user's capacity, the interface becomes a critical point of failure. Highly optimized algorithmic logic provides no value if the user interface prevents the operator from successfully executing the commands. Designing a successful UI involves following measurable, iterative processes and applying standardized heuristic guidelines to evaluate the interaction. Ultimately, the interface is the determinant of whether a software system is practically usable in a real-world environment. To engineer a functional interface, we first look at the underlying architecture that powers it. Every interactive interface operates on an event-driven loop. This pseudocode illustrates the baseline structural loop for all UI implementations. As long as the system is active, it renders the current state, waits for an event to occur, updates the backend state based on that event, and then repeats the cycle. Human input serves as the specific trigger for this await event function. Whether it is a keystroke, a mouse click, or a spoken command, the system halts and listens at this exact node. Once the signal is received, the system responds via the update state function. This alters the backend data, passing the new parameters back to the top of the loop to be redrawn. The point of divergence in the user's experience happens here, in the render function. This determines the specific type of interface the operator will interact with. The first type is the command line interface, or CLI. A CLI requires operators to memorize and type specific text commands. This yields efficiency and granular control for expert users, though it requires a higher cognitive load due to the learning curve. The second type is the graphical user interface, or GUI. GUIs use visual metaphors like desktop folders, trash cans, and interactive buttons. This shifts the burden from memorization to recognition, increasing learnability for a general audience. The third iteration is the voice user interface, or VUI. VUIs remove physical inputs. They rely on natural language processing to translate spoken audio into system events, allowing for hands-free operation. Whether the application renders text in a terminal, pixels on a screen, or audio from a smart speaker, the underlying engineering architecture, the event loop, remains the same. Moving from the architectural loop to a practical workflow requires a formalized approach. We execute this through the iterative UI design process. Step 1 is requirements analysis. Here, engineers evaluate the target audience to map out their specific operational needs and environmental constraints. Step 2 is prototyping. Engineers build low-fidelity visual models to test the proposed workflow and layout before writing production code. Step 3 is implementation. Once a prototype proves successful in testing, software engineers translate those visual models into functioning, deployable code. Step 4 is evaluation. The implemented UI is tested against established usability metrics. If it fails to meet them, the cycle loops back to the requirements phase. During that evaluation phase, we test for 3 core characteristics. The first is clarity. A system is clear when icons, labels, and interactive elements are unambiguous to the user. The second characteristic is consistency. This means enforcing predictable patterns and layouts across every screen of the application. The third characteristic is feedback. The system must acknowledge a user's action, satisfying a psychological need for response and confirming the current system state. These three characteristics serve an overarching engineering goal: minimizing user surprise and ensuring recoverability when a human makes an operational error. A cyclical design process ensures these characteristics are structurally engineered into the final product. To enforce these characteristics, the industry relies on standardized design guidelines, frequently referred to as the golden rules of UI design. These rules are built on heuristics, established rules of thumb used to evaluate and correct the usability of an interface. We can see this applied by looking at this wireframe on the left. This interface violates multiple standard guidelines, creating friction for the operator. The first flaw is error prevention. Destructive actions, like this delete button, are placed without warnings, which invites user mistakes. The second flaw violates consistency. The navigation menus use mismatched conventions and layouts, forcing the user to relearn the visual language for different sections. The third flaw is a lack of informative feedback. Buttons that trigger background data processing provide no visual indicators, leaving the user unsure of the system's status. We can systematically refactor this wireframe into a more effective layout by applying the golden rules. First, we implement a confirmation dialog box for the destructive action. This provides closure and prevents accidental data loss. Second, we standardize the navigation elements, aligning them to a grid. This ensures visual predictability. Third, we add active loading states to the actionable buttons, providing the user with immediate system feedback. By correcting these specific points of friction, the resulting interface on the right is safer and easier to operate than the initial draft. Locating specific points of cognitive friction and applying established heuristics allows for a measurably more effective interface. This blueprint represents the UI discipline. The foundational event loop, the iterative lifecycle, and the heuristics function as one interconnected system. Adhering to this approach provides commercial advantages, including documented reductions in user training time and technical support costs. Furthermore, these standards lead to a measurable increase in human productivity while lowering the rate of system-level errors. The limitation is the resource investment. Following iterative prototyping and evaluation phases requires an upfront cost in development time and engineering capital. Designers also face the ongoing challenge of balance.